Great, so we're going to continue now with our large-scale structures theme, now looking at a new observable. We're going to have Wei Li Pen telling us about 21 centimeter cosmology.
Right, thank you. As Anthony pointed out, this title doesn't have past in it. So 21 centimeter cosmology until very recently had about as much observational evidence as string cosmology or quantum cosmology or any other words that go together with cosmology, but no data. So I'm trying to map out where we have currently gotten to, and hopefully that this is slightly less futuristic than the experimental tests of string cosmology, and what people are doing to make this field a precision field of the near future. So I wanted to start off from the broad brush overview of why some people want to be thinking about 21 centimeter structures, and that's because we've heard over the last few days that the microwave background, which has been the most successful quantitative precision measurement in cosmology, based on about a measurement with Planck of order 10 to the 7 modes. If you ask how many independent things you could measure, probably up to about 10 to the 7 is how many things we have measured so far. And we have almost cosmic variance saturated what we'll be able to do with the CMB. So there's not much more to go, certainly not on a logarithmic scale. That's why people have eyeballed that, well, with 21 centimeters, there are 10 to the 18 modes you could go after. So there's another, 10, 11 orders of magnitude in things you could count and things you could get more precisely. So that's what motivates a lot of these discussions. I think it'll be a little bit up to you to assess at the end of this of how far away we are from getting 10 to the 18 modes. But we are slowly getting in that direction. So let's start with 1. Right now, until recently, it was 0, and that's not a good number. It's a very good number, but not good for doing cosmology. And then there's the practical issues I'll go into of what it does. So is this an analogy of a laser pointer? I push on that. There we go. So this is from a nice cartoon by Matthias and Max some years ago of what the universe looks like. We of course all know that Copernicus got it all wrong, and we really are at the center right here, looking out at the 21 centimeter, at the CMB horizon. So I think Ptolemy would be very happy looking at the screen. And of how far we've been able to see, so these rings are not planets, these rings are redshift rings that we have observed out to. And roughly speaking, this slide is a little bit aged now. Of course, Boss has gotten maybe twice as far as this red curve would indicate. But the broad view of it is that, in fact, in the 21 centimeter, you could map the universe out to redshift maybe 50. It's kind of distance you might be able to map. So there's a lot of volume that is still uncharted. And in co-moving scale, which is roughly what this is, it is actually a misestimate of how much information there is, because the information that you have access to goes as, obviously, the Hubble is just the radius of this plot. But there's a denominator, which is the smallest pixel, that contains meaningful information, which is given as either the nonlinear scale or the Jeans length. This was the smallest scales at which we think we could productively extract information. And that pixel scale gets smaller as you go out. Okay? So in fact, almost all the information is contained out at the very furthest edge that you could map to by a large factor, not just r cubed, but r to the 6 or something is the volume information weighting. Okay, so however far you can get, all information is sitting at the last shell that you're going to be able to observe on this map. So 10 to the 18 is what you get by taking the Jeans math before reionization at redshift, say just around here, or however far you think you can see, and multiplying it by Hubble cubed. Gives you this number of something like 10 to the 18, give or take a few orders of magnitude of what redshift you're going to make this reionization happen at, which is somewhat uncertain. And if you want to think ambitiously, well, with this, all you did is you took like Planck, you can measure something from a Gaussian random field to square root of n accuracy. then square root of 10 to the 18 is 10 to the minus 9, so you might be able to measure something to 9 significant digits, perhaps. If you just plug away, which ambitious, Matthias is right here, when you plug forward, you can say, well, if you translate it into things like FNL or R or something, you get quite small numbers, 10 to the minus 8. In fact, Daniel already has shown that you get effects bigger than that just from scalar-generated gravitational waves, FNL. Just plug in root n, and obviously these opened up in new games that you could think about measuring in principle. There's a lot of in principle in here. But that's, I think, the motivation why people say this has an almost unbounded potential. And then the question is, how far away are we from this unbounded potential, both theoretically and practically speaking? So again, just to classify things that have simulated theoretical interest in the lowish redshift range from 0 to 2. I think interest has been to use 21 centimeter structures the same way as we use galaxy surveys, and that this might just be an economic way of mapping out large patches of the sky. And the standard things people do with galaxy surveys is to try to, we've heard all about it, use BAO, go after dark energy, go after neutrino masses. Those are the standard things that one could do by having a large volume survey. It always seems like a good thing to do more of the same. It's been a technique that's gotten us some mileage. At larger redshifts, we've also heard, if you can measure structures at larger redshifts, you could use them to do gravitational lensing, all the standard stories. At the higher redshifts, where I keep emphasizing, which is where all the information really sits, so this, infinite reservoir of information sits really at redshifts greater than 10. There have been a recent flurry of papers of things you could do to look for gravitational wave fossils and other things. So that's already started to stimulate, at least thinking forward. What could we do? Which is why we come up with these numbers, like this R could perhaps be measured to some very impressive regime. Of course, R could be 0, as we have heard as well. So just because you get 10 to the minus 8 doesn't mean you'll see it, even if everything worked. Now, a technique that I want to introduce that has recently gotten some traction is a concept of intensity mapping with 21 centimeter. So the normal mode in which galaxy surveys are done is you identify individual galaxies, and you cut a little hole around them or whatever, you put a fiber on it, get a redshift, and most of the data that you've taken is thrown away. Like in this Sloan Sky Survey, most of it is empty. You take a tiny fraction of your data, and you take spectra of it, and you painstakingly use these tiny, arc-second-sized objects to stitch together a map of large-scale structures, which has a typical, power spectrum measurement of Sloan, where people have shown at a K of 0.2, those are pixels like a degree in the sky. That's the kind of pixelization you're actually going to bin it down to. So there's a problem with individual galaxies, is that they get faint. Okay, as they get further away, if you want to do this with redshift 2, galaxies get pretty faint, and it gets expensive. You need big telescopes, integrate for a long time, and it just gets expensive. When in fact, it's not actually the galaxy, for power spectrum purposes, the galaxies themselves are not the object of interest. It is these clustering statistics of them. Okay, you want to know what collections of hundreds of them are doing. You don't care about any individual galaxy per se. So even though individual galaxies, by the way, the highest individually detected galaxy in 21 centimeter in emission to date is about redshift of 0.1 something. Okay, that's the highest redshift 21 centimeter emission of an individual object that has ever been detected on its own. And now you say, well, 0.15, let's say, and I'm going to redshift 2. I take luminosity distance, the 1 plus z to the force factors, and you would need a telescope that is, a couple of orders of magnitude bigger than any telescope today. So there have been, ambitious proposals like building square kilometer sized telescopes to get enough photons in to detect individual galaxies out to redshift 2. That is one way of solving the problem, is by building, you can beat the inverse square law by having more metal. Another way of addressing this is to increase your flux. So either increase your telescope, or you keep your telescope size fixed, and you just increase the amount of flux that you care about. And you say, I'm going to bin all those, every pixel may actually, the resolution of radio telescopes is actually pretty crummy. And in fact, in every pixel, there are hundreds of galaxies. So if I don't insist on detecting any individual one, the collective flux actually is not that tiny. And a few hours of integration can actually get you a detection. And as we know from the CMB world, the optimal depth of a survey is to reach a signal to noise of around 1 before you go on to the next pixel. So in the normal galaxy survey game, normally people want a 5 sigma detection to say you've seen something and talk about a redshift of a galaxy. We don't tend to make 1 sigma redshift measurements. For a power spectrum purpose, 1 sigma is a good place to be. You detect it at 1, well, you measure the fluctuation at 1 sigma, and then you go on to the next pixel. So you only need 1/5 the amount of signal to noise, and you've got 100 times more galaxies, so you need about a 500 times smaller telescope than if you wanted to do individual galaxy detection. And this factor of 500 is substantial, right? So instead of needing a square kilometer, you can actually try to do an existing telescope, which is what in recent years, since about 2008, people have pointed out that this might be an economic way of using modest-sized, even existing telescopes to map redshift surveys to a redshift of a few. Now, this is in principle, it sounds straightforward. If all you are limited by is photons and thermal noise and flux, this actually could be, would be quite straightforward. In practice, this is what we want to measure, something like this. Here, again, the thing to look for is not the individual little dots, but the large-scale structure traced out by them. Now, when you actually make a map in the radio, people have done these maps. This is a Haslam map made 40 years ago. This is what the sky looks like. This is redshift 2.5, okay, on the hydrogen line. The structures you see is not hydrogen and not at redshift 2.5. This is synchrotron of the galaxy at redshift 0. These are all within about a few kiloparsecs of us. So this is things right in front of your eyes. The typical temperature here is maybe a few Kelvin is a typical emission. And underneath this emission, there is maybe 0.1 millikelvin, so a factor of 10 to the 4 down from this, there is 21 centimeter structure. Okay? And these telescopes that were used, this was done with Bonn and with Effelsberg and with Parkes, those actually, just by thermal noise, actually are sensitive enough to see those galaxies if it were not for these overwhelming foregrounds, which is what you actually see is this. Okay? What you see is not the 21 centimeter structure. So that's what's been stopping this from happening for the last, say, 40 years. So, if it weren't, we could have done this. This might already have been the only way of doing galaxy surveys, or large-scale structure surveys rather. So people quantify this, and if you calculate, put numbers to this, what a typical foreground to signal thing looks like in kelvins. The single biggest foreground is galactic synchrotron, so that's the single biggest thing you have to worry about. There are other things, point sources, who knows, there are other contaminants, quasars, other stuff. Here's a 21 centimeter signal that you might expect to see. This is at redshift 10, but the whole ratios don't depend much on redshift. At redshift 1, the ratios are pretty similar. Just to put another perspective, the CMB is, of course, microkelvins, so this is still huge compared to CMB. So, reaching a thermal sensitivity of a millikelvin itself is not a big deal, but it's the foregrounds that makes this exercise not entirely obvious. So, in the in a review article in 2010, talking about the 21 centimeter exercise, and there have been telescopes custom built to go after it. The standard law was that what you want is an interferometer with a sparse aperture, so you could do correlations and you could study calibration much better. That was the standard law. So they talk about, in this review article, about telescopes like LOFAR and MWA and other telescopes that would go for high redshift. And they envisioned that once you have detected redshift 10, you could use this to do the more challenging problem of detecting intensity mapping, which is redshift 1, the one I just described. So this was thought to be a next generation type of challenge, really faint collective galaxies against synchrotron foregrounds. Now, history that isn't always all that predictable, so predictions are good to, that prediction was good for about 2 months. And 2 months later, there was actually a first detection using intensity mapping at redshift 0.8, so about the range that they thought was next to impossible. And in fact, even today, this is now we're 3 years later, and there still actually has not been anything like that at redshift 10. Okay, whereas the redshift of order 1 is now able to actually do surveying, and there's actually substantial activity now happening. So I think we're starting to go from 0 measurements to some measurements. And I'll show you a little bit of what, well, it's a bit of a detail of what we've been doing to pioneer this. As I said, there are existing telescopes. When we say modest size, it's a 100-meter size dish. The people at Green Bank tell me that this is the biggest movable piece of metal on land. Okay, not counting tankers and stuff like that. This is the most massive piece of metal that's still movable. So that's our telescope, but it's still a small, of course, compared to the square kilometers. It's a 100-meter dish, not a kilometer-sized dish. And with that, we make a map of the sky. This is at slightly higher resolutions than Haslam. And you can see what the, hopefully you can see what this thing looks like. So I'm going to step through frequency, which is the same as stepping through redshift, and show you a map which is a couple of degrees by, I don't know, 4 by 5 degrees. That's 2 by 5 degrees here on the sky. And what you see is that the sky looks the same at all frequencies. And that's because, of course, all you're seeing is the galactic gradient as a background and some point sources sticking out above the background at 15 arc-minute resolution. This is kind of WMAP resolution on the sky. And one thing you do notice is that at lower frequencies or higher redshifts, these point sources do appear bigger than they do at the higher frequencies, and that's because your telescope resolution is diffraction limited, and you just have less resolution at lower frequencies. And that's one of the headaches, that the maps are the same intrinsically, but not after you run it through the telescope. Okay, after you run it through the telescope, the maps actually look different at different frequencies, and you can't just subtract frequencies from each other. That doesn't, you have to deal with understanding how your response varies with frequency, how your calibration varies with frequency. So the idea of subtracting it does require some more advanced analysis techniques. To give you a comparison, this is what a simulation of the signal looks like. By the way, just to get the idea of scale, this scale here is in Kelvin, goes up to 1 Kelvin, so these bright points saturated are more than a Kelvin. This scale is in millikelvin. Okay, that's a simulated signal consistent with what you in fact see. And here you see, of course, the striking feature that the 21 centimeter structure looks different in every redshift slice. Okay, that's what we're looking for. And the previous one was what we actually see. And this is a factor of more than 1,000 below the structures that we are seeing. And the question is, how do you deal with that? And that's been the basic conceptual challenge in this 21 centimeter detection game at higher redshifts. So what we do is we do a model subtraction. We degrade, we try to understand our beam, try to degrade all maps to a common resolution, try to subtract them from each other. And when you do that, we actually get maps that then look like only thermal noise. Now, it turns out that this map is still a bit shallow. As that's a signal you expect to be about 1 millikelvin. Our noise is still substantially higher than our signal. But again, Kobe had the same issue. The noise was higher than the signal. But statistically, you can still ask, if I stack it all and correlate it, do I see just do the standard things that everybody does, Planck WMAP, of correlating maps taken on different seasons and seeing if there's a net excess correlation in excess of the noise. And then you don't need maps that are very deep to make a detection. And here is what you see with 2 different types of measurements. One is this actually is a correlation of this map against an optical redshift survey in the same field, the Wiggles survey that we've heard about earlier. And you see that the cross power has a substantial detection. I think this is formally a 7 sigma detection of the cross power. So the 21 centimeter is really tracing out the same cosmological structure as the optical galaxies. And that's a good sign, presumably they're all tracing the dark matter we're looking for. So that means, yes, the signal is there, and the foregrounds do not dominate the noise. These noise error bars are perfectly consistent with coming from just thermal noise and nothing else. The thing that, of course, you'd really like to do is make a survey from your 21 centimeter alone without, obviously once you have the optical, why bother doing the 21 centimeter? You can ask, what does that look like? And here's what the 21 centimeter power spectrum looks like from this survey. Just to give you an idea, this line up here is what the power spectrum would look like off the map you just saw initially. And it's just a map, it's just some bizarre averaging of a 3-dimensional huge foreground. Then these two lines, then we clean this, and you saw the cleaned map. Then these two lines are the power spectra of the thermal noise in 2 of our fields, a deep and a wide. And you can see that the thermal noise per mode is substantially above, and the dashed line is the signal expected. And of course, we know how much to expect because we know the cross correlation to optical galaxies. Okay, so we actually know what the signal should be. Here is the current noise. So if all you did is you take the power spectrum of the map, you're up here, and it's a factor of just almost 2 orders of magnitude in power above the noise. And if you average it down by these tricks of correlating different maps to each other, it turns out our statistical noise is about where this red dashed line could be. So in an ideal world, at our integration depths, and this is about 100 hours of telescope time, we could get a 1 sigma detection. Okay, that's the kind of level that the depth has gone to. The data points that you see after foreground cleaning. So out here, there is power. And this power is almost certainly due to residual foregrounds that did not get, because we're subtracting the foregrounds below the thermal noise, and it gets hard at some point. If you don't even know what your foregrounds are doing, you cannot detect anything. How do you subtract them? So we think this is probably limited by the fact that you're trying to dig deep into the noise to remove things that you can't even see. So it's not, we hope that this gets better as you integrate further down. In the best windows, like at higher K, and it's generally understood that at higher K, the foregrounds are less of an issue. There's smaller scales in both in the size on the sky and in the radial direction. And here, the things are consistent with just being noise, basically, you see. So these are points that just cross to 0. These open boxes means that the mean value is actually negative, but they kind of scatter around the red line and are consistent with being due to only 21 centimeter. And in fact, we can put a bound of how much foreground or stochastic 21 centimeter signal there could be, given this data, which is, as we said, it's kind of at the 1 sigma type of level that we can measure these things. But it just shows that we do get down there. Okay, there's nothing stopping us from getting down to the power spectrum, and we're certainly in this range, we're not saturating based on any foreground. And if you now put it into a likelihood of how much hydrogen there is, and now we get both as I said, a lower bound from the cross correlation with the optical galaxies, and an upper bound from the fact that the thermal noise plus everything else cannot be more than the hydrogen we have clustering out there, and we get we get to constrain it within about a factor of 2, which is what you get for about a 1 sigma detection. So this is, means we have our power spectra down to the levels to continue surveying. So I don't know if you want to call a 1 sigma detection or not. That's probably not the right word to use here. But it's now consistent with reaching the levels that you need, and it's a matter of spending more time or having faster survey telescopes. So this has now stimulated a flurry of activity. And there are a bunch of telescopes under construction or under planning or under proposal that to actually map this faster. So the Green Bank telescope has currently that's done with a single pixel detector. And if you've heard in CMB, John was talking about 10 to the 5 pixels. We're starting with 1. Right now they're building 9. 9 is 9 times more than 1. which you've got to take it a step at a time, and that's under construction, hopefully to be deployed about next year on the Green Bank telescope, and then in 100 hours, instead of getting to our level, we should get 3 times deeper in thermal noise. So we should just be making deep maps with the new 9-beam feed. A more ambitious telescope under construction is the CHIME telescope. I'll talk a little bit more about. That has 1,000 beams, also a 100-meter telescope. Okay, so this should be ready in about 2015. So it's currently under construction. It's funded. So that's a telescope that hopefully will just map the whole sky down to a 1 sigma kind of per pixel noise level out to redshift 2. There are other telescopes that are currently other experiments under construction. So the Nancy telescope is building a survey feed. The Parkes telescope has now gotten funding to build an intensity mapping phased array feed to, again, increase the survey speed for slightly lower redshifts. There is a 10-light telescope certainly under engineering in China, which is probably going to go for a lower redshift range than CHIME is, but these are all experiments that are currently moving forward. There are also proposed experiments, one called Bingo from Manchester here, one called Baobab from Berkeley, that have been proposed to do surveys, all in a similar type of parameter space. So this is starting to populate a number of experiments, all based on a 1 sigma detection, which is at least, you got to start somewhere, right? So, so hopefully we'll go from 1 sigma to a very large number of sigmas in the next few years, right? These are talking about in a year, maybe another year. So within 1 year, probably these 3 should be taking data, hopefully, and then a few more years. And so the CHIME telescope is currently under construction for the first phase. Again, we hope to get online later this, I don't know whether, when we say late 2010, it seems to me probably requires 2010 to have more than 12 months, but it's at least not far in the future, with the full thing operating hopefully before too long. It's a drift scan telescope that these cylinders have the useful advantage that they focus light east-west and geometrically, and the north-south direction, they're just a electronic feed that can see the whole sky north to south. And as the Earth rotates after 24 hours, you see the whole sky, at least visible from your declination. And you get to make a map of the sky every 24 hours, and you stack it after a few years, you have a deep map of the sky. And this is in numbers, again, if you're a radio enthusiast, this kind of sensitivity, it does get about a 2 microjansky point source sensitivity per pixel. It's quite a hypothetical number because you're confusion limited way before that. You're confusion limited at probably a Jansky. So this goes 1,000,000 times below the confusion limit, but for time variable sources, okay, you can see if something changes in flux by a part in a million. So these are certainly if you want to look for pulsars, look for transients, this has a very, very fast survey speed on the whole sky. NVSS, the current standard, has about a 2 millijansky all-sky sensitivity on one epoch. So 1,000 times fainter than the faintest surveys today. Okay, that's what we're talking about. Foreground subtraction, a theory going on, and we think it's under control. We've got various. This is what I'm going to say for CHIME. Thinking futuristically, I think I'm kind of short on time here. I mentioned, currently things that have gotten interest are potentially measuring gravitational waves with this technique. It'll require the next generation after CHIME to be able to do something like that, but perhaps not totally crazy. There is a potential redshift range that I think has potential to be interesting. We don't know yet, but in many scenarios of reionization, there is a period around redshift 15 where there could be a strong absorption signal in the 21 nanometer against the microwave background. So, so we are going after a 100 microkelvin signal. At those redshifts, the signal could be 100 millikelvin, okay, on the same scale. So the signal could be 1,000 times larger than what we're looking for. Now, the foregrounds are also 1,000 times larger, so I don't want to try to sell this as being any easier, but it's a similar level of challenge. Okay, redshift, assuming these are models, nobody actually knows what happens, but there's a potential that in this redshift range, with our ability to do foreground subtraction, we may be able to get a tractable, ambitious survey, which would actually be enough to do this kind of R of 10 to the minus 3 or 4 gravitational wave detection, at least statistically. Okay, so this is futuristic, but not, I wouldn't say, I mean, at least I think it's something one can try. If the universe cooperates and technology cooperates, it's something that one can think about. I'm just going to conclude here that 21 centimeter cosmology, I think, is obviously has a lot of promise. I think that's been clear for a while now that the promise is huge. The technique of this intensity mapping of any of this 21 centimeter exercise has now an initial, well, detection in cross correlation and a detection at the 1 sigma, if you want to call that a detection, in autocorrelation, meaning we've been able to remove the foregrounds down to the level we need, this which has led to a number of surveys trying to exploit this to map the whole sky, the whole universe. So this is something which is moving very rapidly, certainly with CHIME and several of the other ones that I've mentioned that are ongoing. I mentioned that I think the thing to look forward to is redshift 1, redshift 10, redshift 15. Those, I think, are the 3 epochs at which there is a plausibly detectable signal accessible with current technology and techniques. And I think this has led to, also apart from the construction and infrastructure that's being built around the world, this also has led to theoretical, more theoretical thought about what we could do. Obviously, it's, I think, important to start thinking ahead. How much money is it worth to us? How much should we invest in such a thing if it were to work? So I think people haven't really thought extensively. I mean, some people here have certainly to think forward of what can we test, what can we learn, how well could we do, what will be the issues in these kinds of techniques that if and when the data comes in, how much further do we want to be taking this? Thank you.
Thank you. Do we have any questions for Wei Li?
Yeah, so you said that maximum way you can go up to the redshift about 50, right?
Redshift up to 50. Above that, the spin temperature couples to CMB, so there is no expected signal.
Then, what is the reason for your so optimistic estimate of FNL? Because we know that, of course, they will be already developing so-called structure. So perturbation will be growing. Therefore, FNL of the secondary origin perhaps will be at least 100, etc., equal 50. So therefore, to go to FNL, 10 minus, I forgot what you wrote, minus 4, which could have primordial origin, for instance, you have to have very good actual methodology of subtracting this kind of secondary non-Gaussianity. This question was analyzed or not, up to what extent you can do it?
Well, I mean, there I would just say that of the existing techniques that people use to go after FNL, some of them are based on local galaxy surveys that are even much more nonlinear than what we're talking about. And, people have clever techniques to they go after various effects like the Dalal effect, and Urs just mentioned a couple, that we can actually get FNLs of a few tens, not 100, but the constraints even from this horrible nonlinear large-scale structure today is less than 100, meaning, it's doing surprisingly well if you pick the right configurations that are robust to nonlinear interactions. That's the goal. Now, I think you do put your finger on an important conceptual question that as an upper bound, okay, I think this is fairly robust. So given that I don't see it, then the sum of my nonlinearity plus primordial is presumably less than this number. In order to make a claim of a detection, okay, then I think you'll really be in the complicated business of, well, what have I detected? Have I detected some not poorly understood baryonic interaction, like there's some radiation physics that's hard to calculate, or is it primordial? And I think that's something, it's think about in any of these aspects, whatever technique you use to go after FNL, because we're already going in the regime where even at the CMB, the effects you mentioned can be a few. Okay, so I think, yes, it's a very important thing to think about. How, if and when we see it, how will we be able to check these things?
At the back.
Some of these issues will also depend on when you first form the first galaxies. Now, of course, there's not much information from, from theoretical point of view. There's huge uncertainty. So, we are actually really groping in complete darkness here. So, so any of this, detailed analysis of what exactly the value of FNL or what is the gravitational waves would depend quite a lot on when do we first form the, first galaxies and how this 21 centimeter couples to the CMB.
Okay, so I think you're asking a similar question as what Slava was asking about, what about all the messy astrophysics that enters? And, some people say, well, go to a redshift of closer to 100 when there were no stars and everything really was dark and clean. But it's getting darker here, I don't know about clean. I think here again, the way I see the more likely initial steps is that as you go forward in redshift, including redshift 1, 10, and 15, things will be, to some level, nonlinear. And you need to come up with, just like with galaxy surveys, right? Galaxies are horribly nonlinear objects, and I don't think anybody promises us to understand galaxies from first principles, of how and where they form. And yet, Matthias wants to understand dark matter, I think, from first principles. Maybe also galaxies. Simon, I think, is closer to understanding galaxies and, in that sense. But that's a program, right? I don't know whether Simon is going to promise you things to FNL of 10 minus 4 from simulations. This would be ambitious thinking to get to that stage. So I think we need to be as clever about finding, like lensing, for example. Your lensing works well, even though you really understand nothing about the galaxies. You can still use it. Very constructive. I think there are techniques, and that's what exactly you want to be thinking about. What can you do that's robust?
We'll take one final question from Anthony.
What do you think about the prospects of doing some of this via CO instead of H1?
CO certainly is an interesting and another promising line that has a lot of flux in it. And being at higher frequencies, there are fewer foregrounds, and one can build more sensitive detectors. Now, one thing I've been encouraging, I'm keeping my hands very busy doing pilot surveys with existing telescopes and actually dealing with the analysis issues. So I've been trying to encourage somebody else to actually pilot the CO intensity mapping with a green bank telescope. That's much bigger than any of these things being discussed, and more sensitive than any of these things being discussed for modest-sized volumes. With CO, there's a much even bigger uncertainty in the expected flux level, because it's an atomic transition, we don't know how much CO there is, and even if we knew, we don't know the molecular excitation states. So the flux is uncertain by an even bigger factor than the 21 centimeter flux is uncertain by. And there, I think, before we embark on building telescopes whose size we don't know how big they need to be, we should look. And I really, I want to encourage anybody to start, piloting this with real data and understanding what's out there. I think that's the concrete first step to take.
Well, let's thank Whaley again.